This is this morning's first plenary talk by Professor Aude Billard. Aude Billard is a full professor and head of LASA Laboratory for the School of Engineering at the Swiss Institute of Technology, Lausanne, EPFL. She was a faculty member at the University of Southern California, my former colleague, prior to join EPFL in 2003. She holds a bachelor and master degree in physics from EPFL and a PhD in artificial intelligence from the University of Edinburgh. Her research spans the fields of machine learning and robotics, with a particular emphasis on learning from sparse data and performing fast and robust retrieval. Her work finds application in robotics, human-robot, human-computer interaction, and computational neuroscience. This research received Best Paper Awards from several venues, among which IEEE Transaction on Robotics, ISS, ICRR, and IROS. Professor Aude Billard has a long list of achievement, but in the interest of time, and so I'm going to cut short, and with a great pleasure, let's welcome Aude.
Good morning, everyone, and thank you very much for the very kind introduction. It's a pleasure to be here. I know I'm in robotics, so I'm going to show you a lot of videos from robots, which is the entertaining part of this morning. I will try as much as possible to give you a little bit of a hint as to what is a difficult problem in robotics and why we think that machine learning is the solution. But I also want to emphasize that machine learning is not the solution for every robotics problem. And so all the work that we do in my lab is a combination between traditional control and then machine learning. We do develop some new machine learning techniques specifically for control, and we also use off-the-shelf machine learning techniques. So I'd like to start, and that's a teaser that I always like to start with, is this problem. Let's try to catch an object real fast within a few milliseconds, and here we're really talking about half a second of flight. And the object is complex to catch. Apparently there is a problem with the video. Yeah, all right, so let's see. Let's see if it plays better now. All right, so the object that we have to catch are flying very fast, but also if you observe that, they are not balls. So that means that they have at least only two axes of symmetry as they have an asymmetry. That means that you have to move and catch it along the main axis of the object. When you catch the racket that you've seen flying, this is even more difficult because you have to catch it at a certain point, which is the handle. And of course, as I will emphasize later in this talk, the major difficulty is that when these objects fly, they fly with very nonlinear dynamics. So you have to sort of model these dynamics, and you have to be able to model it and retrieve this information in runtime. This is where machine learning comes into the picture. But before I go there, I will ask you for a little bit of patience, and we're going to look at the very, very basic problem of grasping in robotics. It seems a fairly simple problem. You will think picking up an object and then placing it somewhere, but as a matter of fact, it's still a very, very difficult problem. And if you look at the way that humans grasp objects, which is here a little list of them, I don't know if we see my mouse, yes, you see different ways in which the fingers are placed on the object. There are a variety of grasp. This one, for instance, is a little unusual for roboticists because the fingers are not around the center of mass. So it's not a traditionally stable grasp. A stable grasp would be something that englobes the object here at the bottom. But you know why this person is handling this object this way is to prevent the leads to come out and to prevent the liquid to come out. There are other grasps like those which are quasi-unstable, especially this one on the bottom, but which are used for politeness when you hand something over to somebody else. And then this is the most magic part, is when you use all your finger, the true dexterity of the hand, to hold different objects. I will not show you any video on this, but this is something that we work on these days. Now, all of this dexterity, all of this true use of all of our fingers in different ways to grasp objects is what is still escaping robotics to some extent. So we try to tackle this problem by saying, okay, let's go back to a problem we know how to solve. We just have a simulated robot here with a cylinder, and a cylinder is a fairly easy shape to represent. And then we will now compute traditional control. We will find the minimum of torque for 3 fingers placed on different parts of this object, such that they're stable, there's force closure, so they manage to cancel the gravity. They're kinematically feasible. You can place the finger. They don't collide neither with the object nor with one another. But that leaves you with a very non-convex optimization. And you'll say, damn it. Actually, this is a strength. And this is a strength that I will use and reuse over and over again in this talk. The fact that it was non-convex meant that it will give you many different feasible solutions. And in fact, it turns out that we don't care so much about optimality the same way as what you've seen for the video, for the image of the grasp in humans. What we care about is feasibility. So we exploited a non-convex optimization formulation. We started it with different initial conditions, and then this yielded lots of different feasible solutions. We ended up with more than 1,000 grasps. And then to make sense of this grasp, we applied clustering. Very simple clustering where we looked for the clusters, with simple k-means, but looking for the likelihood estimates and BIC criterion to find the optimal number of clusters. We found about 14 grasp types. That means that these were clustered and enclosed grasps that were very similar. And I give you a couple of examples. Here is one of those grasps. You see on top, this is the robot, and on bottom, a similar grasp on human. We did not put this knowledge in the robot at all. This is what is discovered by simply sampling all the feasibility space. And so we get lots of them. I'll just show you a few of them here. Okay. But now the problem is, of course, we can solve that at runtime. If we present a new object to the robot, then the robot can go solve the optimization and run for it. But you don't do that. You don't solve each time the optimization. It's like you came to this room and suddenly, like me, you look up at the map and then you thought about it and you did your path planning, but you've done that once or twice. And then by now, if you've been to this room 3 times, then you know your way and you're not optimizing, again, fully from a map. So we thought, well, that's where machine learning can help us. We can take all of these solutions, all the 1,000, we had actually 1,400 solutions, and then we will build a probability map which represents the distribution of all the feasible posture on this cylinder. So this is a 14-dimensional space. It's 14-dimensional because the finger are 8-dimensional, and then the hand position and orientation are another 6 dimension. And then we can populate that, and I represent here a slice which is given by PC. Of course, you cannot visualize that. We learned that by using Gaussian mixture model. The interesting part, as you see here, is that we have a representation of the feasible space, and we also have the likelihood, which gives you a notion of 2 things. It's the amount, the redundancy in the system, the number of postures that are similar. And this is something that we will exploit when we catch objects in flight. This redundancy gives you some certainty that you will catch it even if you have to move a little bit your finger around the object. So we have this manifold of feasible and stable grasp in closed form. We even have in closed form really the boundary, which you can compute, which is the variance across the likelihood. So what happens when we are outside this feasible space, which can happen typically when the robot is not yet on the object, it's sitting there with an initial configuration here. Then we can do a simple line search, okay? Line search guided by the likelihood, and we go to the closest in-joint space, the closest posture that is feasible and doable for the robot on and yield a stable and kinematically feasible posture. And this is what you're seeing here. So of course in robotics, you always have to prove that it works on a real robot, so I show you a couple of examples here. The nice thing also is that we developed that with a cylinder. And you say a cylinder, I mean, how often do you see a cylinder? And we can extend this. In fact, it's immediate. All the graphs that we find can actually be used for many different objects with just a tiny amount of changes. We're simply closing a little tighter the finger on this with a given grasp. Here are other examples. So typically this very nice grasp where you hold the glass upside down, you can use it with a real glass that we see here. This is a real glass just painted for vision, for tracking it visually. And then here is a cell phone, and we can also hold all type of other objects. Right, but the reality is a little more complex. If I put this object in the hand of a robot, yes, it knows how to grasp it, but it still doesn't know to re-grasp it when there is a tiny perturbation, as we see here. So if somebody puts it in the finger and slightly move the object, then it drops from the finger. So in order to teach robots now how to be robust, it's not one thing. Now the robot can find a grasp which is doable, feasible, and it's the closest given this current configuration. But once it's on the object, it needs to close the loop. And if there are any perturbation out there, it needs to be adapting the finger position rapidly. So we can again use learning from demonstration. We could have done that from optimal control, which is a form of learning from demonstration for us, but honestly in simulation it's very, very hard to transfer information about forces, contact. So we want to teach the robot live, and here is an example. So we can guide the fingers of the robot, moving the object in the hand, moving at different configuration, showing different orientation, basically showing the feasible type of constraints, feasible posture in both tactile information and position information. So we record the tactile information of the fingertip, the position of the finger as we do that by backdriving the robot, and then we compute something a little more complex, which is useful for control. We assume that, in fact, we're going to control this finger at the object level. So for the roboticists in the room, that means that we will control now for stiffness impedance at the object level. And we will then have the tactile information here for the finger. We will estimate the center of mass. This is also very strong. We can estimate the center of mass without having it, just by the position of the finger. It's an implicit notion of the center of mass. And we assume that we have a spring to keep the finger along the center of mass, which determine, in fact, the strength of the pressure. And this springiness, of course, will change depending on how you hold the object. So if you turn it around, then you will have a stronger springiness from the thumb than if you have it on the other way around. We can learn again a distribution. This is not a true distribution, this is a drawing. It's a distribution made of all this data, which is just drawn here, which are the tactile data, the stiffness that we infer, and then this length parameter. And what can we do with this? Well, at runtime, what we can do is simply take the expectation over the conditional of this data to determine what is the right stiffness we should have if there is a perturbation, or what is the right posture. So here is what happens. For instance, if somebody pushes the object as the robot holds it, the robot will naturally absorb a certain number of perturbations. All the perturbations that are within the feasible space, which is determined by this distribution, will be acceptable. But this is not acceptable. For instance, rotation, too strong rotation, are not acceptable, and you see the robot stiffens up and brings back the object to this rest position. Okay. The next step, of course, is to be able to adapt to different amount of weight. Don't forget that we don't have the weight of the object. We have it implicitly with this notion of center of mass, which we've computed from the position of the finger. So if we start increasing the weight, like we're doing here, which is the natural thing that will happen if a robot manipulates objects, you need to adapt to this. And here, it's not a very good adaptation. Even though it doesn't drop it, it starts moving a little bit. So how can we then add this notion, this information about weight? Well, we can again teach the robot with different objects, feeding them more or less. We don't count how much we fill them in, no more that we count as we have a glass of coffee or a glass of water in our hands. We just need many different examples. And we add this to the distribution, and we get a bigger distribution. It's a distribution simply that still has these three key notions: the position of the finger, the stiffness at the finger, and the tactile information, the pressure. But this time, the database is larger. And so we get a more informed representation of the data set. And we can, again, condition on this. So you see here, for instance, that we can condition when we increase the amount of weight, then naturally our probability distribution function will tell us to stiffen up one of the finger. If we are a little nasty and we start to pull the object away from the grip, one of the finger, only one of them will actually stiffen up. The one where there is more sliding, I should add that these sensors can actually measure tangential forces. And in this last video, I just want to emphasize once more that with this distribution of feasible space, we also still retain what we had before, which is that the robot will be able to accept a certain number of perturbations, just go along, this is what is called compliance with certain perturbation, and resist or change the behavior, stiffen up, only when it's no longer acceptable. But there are things that are beyond just increasing the stiffness, and here is an example. What you don't see, because it's above, there is somebody here feeding slowly this object with some beans. I hope they are playing. I don't see it. Okay, let me play it again. Yes, there are some beans, if you can see that at the bottom, which are being filled by someone putting some beans inside. And at some point, it will be too heavy. And even though the robot is stiffening up, poof, at some point it falls. But have you seen what the robot has done? In order to regain the stability, it has done something very natural. It has lifted up a finger and then replaced it. And you will say, well, that's trivial. It is not trivial at all. The question is, where do you place your finger? And you have to move it super fast. I mean, here we're really talking about 10 milliseconds, because then when it sleeps, and it's gone. So how can we do that? And up to now, we did not have any information about the object. We did not have any explicit information. We could infer the shape from the position of the finger, but we did not have the shape. In order to be able to move the finger at runtime on the object shape, we need to have the shape of the object. So we can do it a different way. Either we pull a database of object shape, if we can recognize it, or we can get a point cloud and then model it from a point cloud from a camera. But then we need to have, of course, the 3D position, because the fingers are all on 3D measurement. Or we can do it the way that we are doing it here, is that we teach the robot the shape by scanning it. We use the backdrivability of the fingers, so they're flexible, you can move them, and then they slide and they're covered with tactile sensor. So each time that they touch the object, that gives you a position in space, in Cartesian space, which we can compute, and it also gives you a force measurement, which we can use to detect the normal. So with this, we can then learn the shape of the object, traditionally with Gaussian process regression. But what we've done was not to just use GPR, but also to learn a model that could determine the normal to the surface, such that we could put the fingertip on the normal. Now we have the shape of the object, and if there is a small perturbation, as we've seen before, then what we can do is compute a new contact point along this, and simply do a local exploration, taking the gradient along this learned manifold. Quasi all machine learning techniques give you a closed form solution. And so this gives you the manifold of the posture, of the position of the object, and you can slide on this manifold because it's C1 usually, so you can derive it until you have the tangent of the normal. Okay, so that's what we're seeing here, and then we can slightly slide the object along this to retain stability. Of course, if the force is too strong, then what you have to do is jumping, which is what we've seen that, so I'll replay this. Too strong force, then you have to quickly jump, which you can do also if you have a fast hand and if you have a complete representation of the object and the feasible posture on the object. So you have to understand that this combines both the feasible space of my fingertip as well as the modeling of the surface. And here are a few videos of this. So we tested the system. Actually, it's too bad that it's playing so poorly here. Let me just play it again. Hopefully it will not shake. It's supposed to shake, but not as much. So this is a strategy that we've developed, was to shake object in the hand. It's something that is a benchmark now used in robotics, to shake the object to really see for how long can you hold the object in the hand. And you see on both videos here on the left-hand side, the finger slides on the object because they're large enough, and here they have to jump because it's too fast. I would like to also emphasize that here on the left-hand side, we had trained it only on the first bottle, a simple bottle, this one, but then there was a generalization, a natural generalization to other bottles. I don't know why the videos are shaking that much. Is there a problem with the projector? The refreshing, okay. Well, moving on, so another thing that we've been working on a lot on is to develop prosthetic control. And here is an example where we can detect from EMG data. This is, of course, classification. We compare many different classifiers to detect different type of grasp, as you can see here, so that the hand, if this was a prosthetic hand, could grip different type of object. And on the bottom here, you see collaboration done with Northwestern University, where we apply that on actual prostheses. To prove that we could use this control system, we then worked some more. Now this is done jointly with Silvestro Mechera, who does the decoding using different neural networks for decoding precisely the position of the finger to detect the position of the finger on the bottle as you carry it. What happens if you only use, as we see here, EMG data for carrying the bottle, is that you don't have any information fed back to the person who is using EMG about the tactile information. And again, these tiny slippage that are so quick will happen, that's sure, and it will drop it, and you will not be able to retain from that. So when we combine both the detection with EMG and the controller that I've presented before, which enforce that we will actually close and stabilize the object as we move it, then we have a very, very stable control, which is moving this way. It's very sad that it shakes that much. Do you have any suggestion? Should I get out and start again the projection, maybe? I've lost the screen. Hello? Come again? Yes. No screen at all. But if there is an urgent question, I can take it now.
Yeah, so let me see. Kevin upstairs?
It's back there, but
Yeah.
okay. All right, let's go there. All right, we're going ahead of ourselves. All right, you haven't seen any of that? Okay. Okay. Okay, that seems much better, yes. Okay. And now you have a stabilization which is done as the person carries the object and put it back now on the table. So we could prove that, that it will really enormously improve the success rate by really enforcing that you have a stabilization at runtime. So now we have many different aspects that I've presented, the ability to restabilize the object, the ability to determine where to grasp the object, and all of that is in closed form, or we can very quickly do a line search to find the closest point. And so I'd like to go back to this, which was the teaser to start with, is how can we then grasp things that are flying. So to do that, the first thing that we need, of course, is to be able to predict where the object is flying. And the difficulty, as I mentioned in introduction, is that the object flies with a very nonlinear dynamics. And it totally depends on the initial translational and rotational velocity. So you may have very, very different paths, and what is difficult is that you have to predict it so that you can align with the handle when it comes to you. And you really want to grasp only the handle and not the large part. So in order to do that, we simply flew rackets and we tracked them. We track them with a very fast camera out there, and we put markers. And with this is a slowed-down version to appreciate that we really made sure to spin the racket so that it will have a very nonlinear trajectory. Then we contrasted many different ways of predicting the dynamics, which you see here. And the winners were neural networks as well as support vector regressions. But we chose finally support vector regression because the one problem with a neural network is that we needed to predict ahead without having any data. So we needed to do a forward planning. And it will drift, as you see here, the blue line. It could drift very far from the data very, very rapidly and give completely nonsense. And so that was a bit dangerous because then the robot will suddenly predict that the object will get to a very large place and start moving in a very different direction. SVR was a little less accurate, but it was fastest also, and it drifted less, which was less dangerous for this application. So we ended up using SVR with RBF kernel. And the good thing also, again, is that it's closed-form solution, and so we could derive it, and then we could put that in extended Kalman filter. Now, we need to grab the object. I've told you about how we can grab object and represent that. So what we did was to represent the way that we should put the finger on the object by having human sampling from this, and this created a sample distribution that you see here, a slice, and it's a bit the same as what we've seen. It's a simpler distribution because basically it's a cylinder. So it's just learning the extent to which you can place your finger. And this is sort of a region which is feasible. That means that any of this region is doable for the robot. Now we have the trajectory of the racket, which is flying in space. We know the workspace of the robot, and so we have to determine where to grab it. And as you can see it, for a while, usually the racket flies within the workspace of the robot for some time. Sometimes means usually 10 milliseconds, but it's still good. So we have to choose now, do we pick it there right away at the beginning before it's gone? At the very end, probably not such a good idea, so maybe in the middle. Yes, but this depends very much on something else. And this something else is what is doable for the robot in its joint space, which is what we call the inverse kinematics. So for that, we also built a representation of the joint space of the robot, which is illustrated here. And then we will compute the most likely position and question, is this the most likely one? And the most likely one is the one the densest. And if it's the densest position, that means that this is the one where I can rotate or change slightly my position, which is very necessary because as the object flies, I will have to adapt to position and orientation. And so I better be in a region where I have many different rooms. It could be that this one in the middle is good, but maybe I'm at the edge of my joint space, so it's not such a good idea. So we combine this notion of probabilistic distribution of the workspace of the robot with the trajectory planning to determine the best grasping point. And now we can compute a path to get there. But the reality is, of course, a bit different. It flies so fast, even if we have very fast camera, and we have this forward planning, which is fairly good. What happens in reality is that as we're starting moving, we make a different measurement, and then we determine that, in fact, it's not flying where I thought it would be flying. It flies somewhere else. So the question is, how do I adapt? I just have computed the flight, the complete direction of motion, where I should pick it up, what is the most likely, and now, poof, I have to redo that at runtime. I can do this, but the problem is that I have to compute the best position. So the question is, how do I compute now an infinite number of paths which will lead me to this in closed form? This is a talk that I've given at ICML. This is why I chose not to repeat it here. So if you're interested, you can look at it. There's a lot of machine learning being used for doing control. So what we do is that we teach the robot, we show to the robot, for, like here, different trajectory in space to grab a racket. And what we do is that we build what we call the dynamical system. It's a first-order equation, which resembles like this. It's a field of motion, which is known in closed form. And this is a combination between machine learning techniques as well as control constraint from control theory. So we can enforce that this flow will be stable, and we can also enforce that it's closed form. That means that at runtime, I have many different trajectories. I can further put something, which is the frame of reference, on the object, such that it moves with the object all the time, and the frame of reference is attached on this flow. And so what happens is that when there is a real measurement that goes to some other places, then I simply move both the flow and the center, so the origin of the system. And so this is a natural way in which I can recompute the path. In fact, the path is given to me in closed form, so there is no planning. So we are again in a closed form solution, and this is what allows this real reactivity. So, and here are, of course, many different videos showing the system working live. So you see, maybe you can appreciate that the trajectory each time is fairly different. As we throw the object, then the robot has to start moving right away. This one I particularly like, the one with the bottle of water, because it will. Decidedly, I've tested all this video. I think it's really a problem of screen. But it can catch also this bottle of water flying. You can find all of this video online if you're interested. This one is particularly nice also because you will see that it will catch the object when it goes on the side. Okay, so you see it's a very different trajectory. It has to go down. And there are lots of adaptation to be done, of course, when you're catching the racket. Another thing that we've extended to was to be able to catch something that falls. You say it falls, it's much easier. The dynamics of the object is relatively simple. But still, there is a problem, is that if it falls, as we see here, then you think that you catch it at the top, but suddenly, for a tiny, tiny little change, poof, you should catch it at the neck. And you see there are two attractors, one at the top and one at the neck. And you say, why are these two different attractors? They are different attractors because the aperture and joint space is very different. These are two different grips. And so in a few milliseconds, you have to decide, do I catch it at the top or at the bottom? This was also another thing that we had developed that was published at NIPS. We showed that we could actually learn an automatic partitioning across different dynamics in space. We could learn both the partition that you see here, okay, and also learn a dynamical system for each of those partitions to grasp different attractors. And this could be learned in conjunction with the different grasping point on an object. And so this could be used then to in fact, grasp an object. And this is a little bit illustrated, as you can see. This dynamics, which is embedded in the brain of the robot, is actually turning, moving with the frame of reference of the object, and letting the robot switch across a different dynamical system. So I'll show you a live video here to catch a bottle. It lasts for 0.2 seconds, and the robot has to choose between catching it at the neck or catching it at the top. And so it completely depends on the orientation at the beginning and the way that it's flown. So it may look as if it's slow, but if you look at it from the perspective of the robot, which we will see in 1 second, as we come very close, then it's really extremely rapid. And so we have to take into account that the robot also has some inertia and has to jump and really cruise it on the right position. We move that one step further to have two robotic arms grasping in conjunction an object. So same thing, we can have a trajectory for the object. We can have the two workspace of a robot, which we can compute the way that I've described before. And then we can determine grasping points on this object and compute what is the most likely point where the two robots could grasp the object. And this is what we used for RSS to catch a flying object. Here was a particularly difficult object because this object is non-rigid. And so you have to keep tracking and keep updating, in fact, the dynamics of the moving object. What is interesting also is that the two robots are really synchronized, and they're synchronized, but they don't follow the same path. And at runtime, they're just computing a different path thanks to the dynamical system to be able to reach these different points in synchrony. All the control we've done that I presented at the beginning was control implicitly in force. So we were controlling at force at the fingertip. Then we moved to be able to control for dynamics, for something that moves and put its hands on the object. Now, of course, what we did here was to extend, so this coupled dynamical system, these two robots that can grab an object, can also control for the force the same way as the finger. You can think of two robot arms here as two fingers, which is very similar to what I presented. And so they have a natural robustness to perturbation, which is inherent to the dynamical system, which allows us to break the grasp whenever we want, as you see here, and have the robot come back, and then they align. So they adapt constantly to the position and orientation of the object, but they also stabilize for the force. So if you change the orientation, for instance, or if you push the object from left to right, then they will adapt to the forces. So there are lots of very interesting applications. One of them, which was presented at AAAI just last year, was this one. It was to be able to guide, in fact, these robots using a foot interface, such as to leave the hand free. That's what we're seeing here. So the two robots are now coupled. They control for the force that they're applying here on the object. So they hold stiffly an object, and even though the person is doing some manipulation on this object, they compensate for the force. And the foot interface that you see below there is there only to help move the orientation and position of this coupled system. So it's one way of using this grasp, this stable grasp, the adaptation of the robot grip in conjunction with the direction which is given by the human. We have started developing this for application for surgery, which I show here briefly, but I was presented also at AAAI. So there, the idea would be to have two robotic arms supporting a surgeon. And so these two robotic arms also have to synchronize and stabilize and hold stiffly different objects. It brings us also to another problem of control that I don't want to tackle here, but which we're working on, which is controlling for soft and deformable objects. But here you have just the first video. This is really work in progress. There are two feet interfaces that control for these two robotic arms. One of them is controlling for the visual feedback, which is given here through a camera. And we mimic a little bit what will happen when you do surgery inside of a womb. The person has his two arms there inside to do his suturing. He's suturing here on a plastic elastic. And then one of the robots controls for the retractor to hold the object in place. Finally, I guess I'm running slowly out of time. Of course, in robotics, what is particularly interesting is always to scale up, to bring things to more and more complex level. So it's one thing to balance with fingers in the hand. It's one thing to balance with two arms that are fixed on a table, but it's a terribly difficult thing to balance things when you're actually walking. So we started doing the same thing now, balancing, holding stiffly object while we are balancing a robot. And here is a particularly complex one, which I chose on purpose, which is that the robot, we'll see here, has to go down, 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 so almost unstabilize itself, pick up the object, and then bring it up. Now we created perturbation. This is in simulation, and we asked the robots to be able to adapt to this different perturbation. So as soon as it sees that the object has moved away, then it comes closer to the object and tries to grab it, goes down again, and then off we will create again a perturbation just when it's about to close, and then you have to go back. So what is illustrated on the left is a sort of it's a transition across different dynamical systems, different controller, which is controlled through pre- or post-condition, but there it was fixed, but one could also learn it. So I'll show you live experiments, just to show again that this notion of grasping and stabilizing can also be applied now in conjunction with stabilizing the full body. We see here that the robot is holding a box, and by the way, this robot can hold 400 grams at maximum, so this box is not very heavy. but it's heavy for the robot in comparison. And so really, we place the box not in a nice configuration where the robot is already stable. We force the robot to destabilize itself, and we also apply some perturbation once the box is being held, as you can see here. Furthermore, we can just test also the ability of the robot to adapt to different configuration of the box, to restabilize itself as the box is being moved just before it grasps it. And one thing that's particularly interesting here, as you can see, is that when the box goes too far, then the robot detects the same way as what I've presented before, this notion of feasible grasp. It detects that it's not in the feasible region anymore. Even if it does a line search, it will lead it to an infeasible posture for itself because it will be outside its gravity, and so it will not be able to reach that. So we moved one step further. We included walking and navigation, what you've seen before. Oops. Okay. And then when combined with navigation, we have the system that you've seen just in simulation before, so that the robot can adapt. That's what we had there. If we move the box, then the robot will start walking again and go to the box and close the hand. The robots here can handle carrying a box together with someone with all the instability that are generated through this. And it can also handle being moved as it comes close to grasping the box just on time. So with this, I will stop here, and I will just make a quick summary. All of the work that I've presented here is available on our webpage. It's available as source code. We also have tutorials. We have publication and videos. And I want to thank, of course, all the people who worked behind that. There are the people who worked a lot on the catching object in flight. Sina and Nadia especially for all the modeling of the combination of coordination of the arms. The learning and manipulation, the robustness was done by Miao and Huang. And then all these people were behind the control of the humanoid robots and also the stable control in compliance with the humans. With this, thank you for your attention. I will welcome questions.
Sorry. For people who have questions, if you could go to the mic in the pathways, that'd be great. So while we're waiting for people working up there, I actually do have a question. So I'm not a roboticist, but I have seen a lot of work on using deep reinforcement learning, particular learning control policy end-to-end using visual images and directly go to a controller. And my impression from your work is this is not a typical approach you would take. What would you contrast this approach and highlight your philosophical thinking about general direction along this line?
All right, thank you for the question. So it's true that, well, first of all, we try to learn from sparse data and especially from real data. So in order to do that, it's fairly difficult to do that with deep reinforcement learning because you will need to do simulation. And a lot of the work that I've shown requires to actually have control over the force and the friction. So we need to really be with a real robot. That's one thing. A second thing that I have illustrated a little bit here is that we try as much as possible to have a closed form and completely understandable model of the dynamics and what has been learned, so that it's fairly easily interpretable in a way by construction. So that's maybe the major difference. But we have used reinforcement learning in some cases. We did not see for the type of problem that we have the need to go to very complex and deep model because often, in fact, we already know to a large extent what is the control system that we need, and what are we missing is the dynamics around it, the dynamics of the data.
Great. All right, I think we have people lining up after.
Okay, so thank you. This is beautiful. I wanted to ask how you would handle an even more difficult problem where you want to catch like a fragile object, like maybe an egg that you don't want to break.
Yes, it's a very good question. I don't have the slides here, but one thing that we developed, because the problem was that when we catch the object, we're actually stopping. So the interaction force is super strong. So, but I did not present it here because it's more control. So our strategy that we've developed was to actually move with the dynamics of the object for some time. We have published that a couple of years ago. And it's actually very interesting because it applies also to space. So you put yourself a little bit in orbit if you want. So you know the dynamics of the object. You move with the dynamic of the object. You make a first contact, and then you slowly close the object, close the hand on the object such that you really reduce the forces. At runtime, we try to be able to control for the force when we're catching, but the problem is that we just don't have the time. So few milliseconds that even if the hand is super fast, there is no time to actually change all the impedance. And if we make the hand really very compliant, the chances are also that we will simply not have the time to really close on the object. So yeah, just this strategy to fly, to move with the object is fine. We actually even did it with the humanoid robot, where the humanoid robot will actually get the object like this, which is a strategy that you see in humans. And then, absorb. So basically the body and the motion of the body creates a sort of compliance which diminishes the contact force.
Thank you.
Thank you. Very interesting and impressive work. One question I had was that you showed examples of bottle and tennis racket, right? So is there some learning that you can transfer from, for example, what you are learning about the bottle to the tennis racket, or are they kind of to be trained right from scratch?
I cannot hear.
If you don't mind, just closer to the mic and repose your question.
Is this better?
Well, we could not hear very well. So is the question how to transfer?
Yeah, so I mean, you learned from, let's say, for example, with the bottle, and then you try to, let's say you don't do any training for the tennis racket. How much does it still work, and what are the parts that will not work?
So there are things that do not transfer so well. So for instance, the learning of the dynamics of flying objects, we saw that, for instance, a bottle of water which is half filled will fly completely differently from a bottle of water which is completely empty. And so, we could not transfer directly. You could bootstrap a little bit the model and then relearn and require less data, but it's not so trivial, unfortunately. So that's a weakness. For learning the stability in the grasp, there was a lot of transferability. In fact, if you recall, we started learning on a cylinder, right, and then it transferred to many different objects. And we also learn on different bottles, and then they will transfer also to larger and smaller bottles. So there is some transferability, but not all of it. I think in the end, indeed, one needs to see more and more objects. It's something that I find is a missing point in the work that we have currently, is really to be able to now create a complete knowledge, complete database, and then really build from one to the other. That is really something I would love to have. It's basically the lifelong learning that Troon coined already many years ago, and we still don't have it. It's not so easy. So I thank you for the question. I think it's a little bit the hurdle. Generalization, we have some generalization in some parts. I still believe that one cannot generalize for everything, but how to then build really a large group of knowledge and then pull from this knowledge at runtime for different type of skill, for different computation, that is something that is still a little bit missing.
Yeah, especially while not forgetting what you have learned earlier, right? When you get to new environment, don't forget what you learned earlier, completely change the behavior for the new environment only.
But it depends what is the new environment. It depends how much it has changed. Really, we focus a lot on disturbances. And there are still very few groups, in fact, in robotics that actually disturb so much the robots. Bump into them, push what they have in the hands, put more liquids, less, etc. It seems completely trivial, but if you look at most of the robotics video, it's a fairly constrained setup. Okay, with everything, nothing's moving, and so. So I think this is a change in the environment. It's a change from the initial condition to which we are fairly robust, but not to end completely. Very, very different changes. We have done. I should have taken this video. We have done things where we take one object off the hand and we put another one in place, and there is some adaptation of the grasp because of the stability and the virtual frame of reference. But yes, so I don't know what you have in mind in terms of change of environment. Maybe you can discuss it offline, but
sure.
Yeah.
Thank you.
I guess we have one question for a very quick question and answer, hopefully.
Yeah, hello. I just wanted to ask how biologically plausible is the way of how you solve these grasping tasks? and problems. Like, I mean, many animals and also humans, of course, they have solved this, right? They can do that very quickly and catch things. I just wonder how plausible is it that biological systems work like this, or
I see, I understand.
you might not care about that.
So first of all, humans are really bad at catching objects like those. You can try it. We actually have funny videos where you throw a bottle or you throw, I mean, you can train yourself. So there are people who throw at each other knives, okay? But usually it's a pair of people, it's a pair of people working in circus, and they've trained each other. And they know how to expect the knife to come up. But if I just now take something and I throw it at you, there are very little chances that you will catch it. Or you may catch it with a strategy, which is the englobing strategy. You may, grab it with whatever you can.
Yeah.
So no, I think in that sense, it's not really representative of what human can do, or maybe what human could do after a lot of training. But and I've spoken fairly little about that on purpose because I've given the other talk about dynamical system and machine learning so often that I wanted to shift the topic. But in this other approach, I mean, everything that we do is dynamical system control, coupling of dynamical system, stability. This is inherent. This is the way that we describe human motion. So I cannot say that this is the way that the CNS controls, the central nervous system controls humans, but certainly an approach, a computational approach that has been used to explain human motor behavior for a long, long time. So in that sense, it is close to the way that humans control their body, or animals at large. In fact, it makes sense because these dynamical systems are completely time invariant. And so they free us from time, which is what we are doing on a regular basis, is that we don't use this, we just use relative position, relative movement from one person to the other. So it's a long answer to a short question, I'm sorry to say that, but there is no immediate explanation of how the human body works, but you can see that there is a huge amount of inspiration from it.
Yeah, definitely.
All
it's
right.
just amazing, I think, how dogs, for example, can catch something.
Yeah.
And they don't have a 3D tracking system with infrared cameras and all this stuff.
Yes.
So it's pretty amazing.
All right. This has been a great talk and discussion. Let's thank the speaker again. It's fantastic.
Thank you.
Yeah.